My topic is IC security. The first topic is manufacturing risks. Security risks can broadly be broken up into two categories. The first of these is manufacturing risks, which are risks incurred during production or development. These risks are usually based in manufacturing facilities and include unauthorized overproduction, IP piracy or reverse engineering, and the potential insertion of backdoors or trojans into the circuit. The second category of risks is post-production risks, which require the contents of the chip to be secure after it is manufactured. Some of these risks include side-channel attacks and fault injection attacks. Manufacturing semiconductors is a very expensive and involved process, which means that many companies must turn to a third party to manufacture rather than doing it themselves. Because of this, they lose some of the trust and oversight that they would have if they manufactured in-house. Manufacturing plants can overproduce chips or manipulate the yield information of the process to develop extra chips which can be sold illegitimately. There is also a risk of defective chips being sold and underperforming. Since manufacturing companies have access to the design information used in the manufacturing process, there's also a possibility for them to reverse engineer the chip and reconstruct the schematic to clone it or even modify it, inserting malicious components like a backdoor. There are several strategies to preventing IP piracy. Logic obfuscation transforms a design so that the original circuit and functionality is hidden. The correct functionality of the chip can only be determined using an obfuscation key, which is secret and programmed into the chip after production. This key reverses the transformation to restore the original circuit. IC metering allows designers to track chips after production and only activate desired chips. This can be accomplished through unique IDs or exploitation of process variations in silicon. Hardware watermarking attempts to prevent IP piracy by marking a signature within the chip that allows identification of the designer. Split manufacturing divides the manufacturing between two facilities, where one facility manufactures the higher metal layers and can be trusted, while an untrusted facility only manufactures the lower metal layers and transistors. With this approach, the untrusted facility never has access to the full layout of the chip. Camouflaging cells replaces individual logic cells with cells that look similar but function differently, which can prevent reverse engineering by making it very difficult to determine the actual functionality of the chip. The diagram here shows a design with two camouflage cells, which result in 4 different potential outputs, depending on what combination of the two the design actually contains. Some reverse engineering attacks that are commonly used for evaluation of the security level of countermeasures are the brute force attack, a greedy attack, and a satisfiability attack. The first is an exhaustive search of potential obfuscation keys that takes advantage of the key being spread across the design. The key is distributed to maximize obfuscation of the design. During testing, sequential logic is converted to multiple stage combination logic in a form called scan chains, which allows an attacker to try all different key and input values to monitor which produce the correct functionality of the chip. When the logic is too complicated for a brute force attack to be realistic, another attack that can be performed is the greedy attack. The greedy attack uses an unlocked chip as a reference, and the same set of patterns are applied to the locked and unlocked chips. This attack can rule out potential keys if the results between the two chips do not match. This attack is very effective on more complicated circuits, but requires the use of an unlocked chip to be performed. A satisfiability attack attempts to satisfy output conditions given a specific key. The diagram shows 2 obfuscation approaches, A and C, a timing diagram for manufacturing tests, B, and the scan chain attack in D. A solution to the problems with traditional obfuscation approaches is the Design for Security, or DFS, architecture. This architecture is a unique approach to obfuscation that has several secure features. The netlist is obfuscated and requires a key to be activated, but all testing and analysis can be performed without access to the key. In addition, the unlocked circuit blocks scan capability, which prevents greedy attacks using a reference unlock chip. After being unlocked, tests can still be performed, but they require access to the key. The key is never stored on the device, which prevents it from being read from an unlocked chip. The key gates are evenly distributed across the design to better obscure the design and prevent logic-based attacks. The DFS architecture uses a secure cell to protect the key and still allow for testing. A multiplexer is used to select the functionality of the circuit. Once the key is programmed into the circuit, it can persist as long as the SE pin stays low. This also allows further tests to be performed after the key has been programmed. The test pin is used to enable scan-out capability. The diagram below shows the architecture. Another technique used to prevent IP piracy is camouflaging. Camouflaging conceals functionality by using logic cells which look alike but function differently. This prevents reverse engineering by concealing the actual functionality of the chip. Camouflaging techniques usually fall into one of three levels. At the fabrication level, doping-based and contact-based techniques are used to create always-on or always-off transistors, which hide the circuit structure. Cell-level techniques use lookup tables with multiple possible functionalities to hide the end functionality. Gate netlist level techniques use cell insertion algorithms with given constraints to attempt to make reverse engineering as difficult as possible. These algorithms input cells or connections and prevent more advanced techniques. The diagram shows an example of two camouflage cells, where the functionality of the circuit depends on the contents of the cells. Security of camouflage cells can be evaluated through several factors. The first, decamouflaging complexity, refers to how many input-output patterns are needed to determine which functionalities are false. It can be determined through the number of possible functionalities and uses a satisfiability-based strategy, assuming an attacker would be choosing patterns selectively to optimally determine the true functionality. Other ways to increase the security of a camouflage cell include increasing the number of possible functionalities, which makes the true functionality harder to guess, or increases the Hamming distance between functionalities, which creates greater overlap in the potential outputs. The diagram shows a camouflaging design flow, showing the different steps in the process. The goal of camouflaging strategies is to keep them as low overhead as possible while still remaining functional. The amount of overhead generated by camouflaging its cell depends on that cell's functionality in the circuit. Two methods of increasing the number of possible functionalities of cells are XOR type camouflaging and STF type camouflaging. In XOR type, seen in part A of the figure to the right, an extra overlap is created. The contacts on the right can then be modified to be real contacts or dummy contacts. Different combinations of which contacts are real and which aren't can alter the functionality of the cell to be either inverting or non-inverting. The strategy can be applied to different kinds of cells as well. STF type camouflaging uses doping to create always-on and always-off transistors, which are difficult to detect. This strategy is seen in part B of the figure on the right. In the figure, changing the doping scheme converts a NAND cell to an inverter. An AND tree is another strategy, which uses a tree of AND gates where each input is camouflaged. This approach can be proven to increase security when combined with the XOR and STF camouflaging methods. The decamouflaging complexity grows exponentially as the tree size increases, making reverse engineering attacks very difficult. Next is side-channel attacks and side-channel attack resistance. Side-channel attacks rely on the idea that ICs leak information during execution, and that information can be monitored to determine characteristics of the circuit. Three of the most common variables to monitor are execution time, power variation, and electromagnetic radiation. These attacks are not expensive and not intrusive, meaning there is a relatively low barrier to be able to perform them, and as a result, they constitute a very high risk. The strength and security of the algorithm or protocol being used is completely irrelevant if the side channels are compromised and information is still leaked. Side channel attacks that monitor execution time or power consumption are relatively easy to avoid by balancing capacitances so that fluctuations in power are not data dependent, or by structuring logic so that all outputs arrive at the same time regardless of value. A more difficult attack, known as differential power analysis, exploits the inherent data-dependent characteristics of CMOS technology. As seen in the figure, depending on the change in input value, the response of the output capacitor is different. By monitoring the variance in these output capacitances, the input data can be read. This method relies on statistical analysis and error correction for optimization, and it is more difficult to prevent. The priority in designing side-channel resistant circuits is to classify different signals by whether or not they are sensitive. For example, an encryption key is a sensitive variable. Protecting these sensitive variables from side-channel attacks is then a design priority. There are several countermeasures available to deal with side-channel attacks or differential power analysis. One is to reduce the signal-noise ratio by either increasing the randomness or adding noise. Masking, which replaces sensitive variables using a random variable mask, increases the randomness of the circuit. Another strategy is balancing the leakage of the circuit. One way to do this is with dual rail with precharge logic, or DPL. DPL signals use dual rail pairs to transmit signals, where one rail represents the signal and the other corresponds to an inverted signal. This makes the true value harder to determine. Another important characteristic of an SCA-resistant circuit is reduced or eliminated data-dependent power variations in the CMOS devices. Two characteristics of data-independent logic are that the logic is differential, which means there is no difference between the power variation in a charge event and a discharge event, and that it is dynamic, which means that the consecutive events are independent. This is usually accomplished by resetting the cell each cycle. In addition, capacitances are balanced to reduce leakage even further. The diagram on the right shows one balanced layout known as sense amplifier-based logic. Another type of layout is called wave dynamic differential logic. This circuit style is both dynamic and differential. A pre-discharge reset wave is alternated with the evaluation waves to allow for the dynamic logic. It is integrated during regular synthesis and improves on prior techniques by being easy to implement and using existing technology, and using a small load capacitance and supply current. This means that the signals are stronger and that it requires less power. The load capacitances must be matched so that the amount of capacitance charged stays the same. The diagram on the right shows the difference between a static CMOS implementation of an indoor invert 32 cell and a wave dynamic differential logic implementation. Multiple differential pair routing is a routing strategy that uses routes which are parallel and in the same layer. As a result, the two routes will have the same parasitic effects. The routes are shielded with power and ground lines to eliminate crosstalk between wires. This can also be solved by increasing the distance between different differential pairs. Usually, differential pair routing is used for critical signals like clock or reset signals, but a secure design, such as a cryptography application, requires many signals to be routed using differential pair routing. As a result, tools capable of this kind of routing are limited. One solution to increasing a circuit's side-channel resistance involves using a secure digital design flow. This process uses WDDL logic and multiple differential pair routing to reduce or eliminate the information leaked through device power characteristics. The design flow can be seen in the figure on the bottom right, and it's algorithm independent. It only requires two extra steps: cell substitution and interconnect decomposition. And other than that, it does not modify the design process at all. The actual circuit design and functionality is not changed and requires no additional modifications. In the first new step, cell substitution, all output wire pairs are abstracted as one wire. These are routed with fat wires, which can be seen in the figure on the left side. This happens at a gate netlist level. Each gate is replaced by the WDDL equivalent, and the output wires are paired. Inverters are removed and replaced by switching the nets, since all signals are now paired anyway. This netlist is then used for the place and route step. The interconnect decomposition, which happens after the place and route, converts the abstracted fat wires into wire pairs. This process can be verified in the same way as the normal method, since WDDL gates are functionally equivalent to their counterparts. Timing attacks use timing information to look for variations which may depend on data, a process that could leak information about the secret key. This attack does not depend on power variation, so even in a design where data-dependent power variations are limited or removed, timing must be managed, usually by making sure that a worst-case running time is maintained across all data paths. In traditional designs, power analysis can also detect idle cycles used to maintain running time, but using the secure digital design flow, every gate has a switching event in every cycle, meaning that idle cycles cannot be detected. Electromagnetic attacks target the flow of charges in the device, which are different than power analysis attacks since they are more localized and power attacks are more global. A sample measurement setup can be seen on the right side. Electromagnetic attacks are much harder to perform than power analysis and require more specialized tools. Since the differential wires are placed very close together, it makes it nearly impossible to determine which signals are coming from which wire, meaning the data is not readable. The scale of distance between wires is on the order of 1 micrometer, while the lengths of those wires are on the order of 10 to 100 micrometers, and the measurement probe is placed on the order of 1 to 10 millimeters from the device. The design is also resistant to fault injection attacks due to the redundant encoding in WDDL cells. Each state is represented by 2 bits, so error detection is possible. Next are fault injection attacks. Fault injection attacks rely on the ability to insert data into the circuit. This data can be used to force errors, which may leak information in the form of power draw or timing violations. Countermeasures to fault injection often rely on redundancy. Redundant circuits allow for error detection or correction, since an attacker would have difficulty producing the same fault in multiple areas. Increasing redundancy and providing redundant redundancy checks also increases security. Using dual rail with precharge logic, where each signal is paired with an inverted signal, also provides redundancy, since an attacker would need to modify both signals. Infective countermeasures detect faults in real time, and if a fault is detected, the ciphertext is randomized. Since an ideal ciphertext is indistinguishable from random noise anyway, it is impossible to detect that the ciphertext has been modified at all, but the data is not recoverable. Last is a discussion of the response of CAD tools to these countermeasures. Using automated CAD tools during the VLSI design process can compromise many of the countermeasures discussed. Since most countermeasures add logic, there are many situations where this extra logic can be optimized away or made less efficient. Especially in the case of redundant logic, CAD tools do not know the security application and just see a redundant cell that can be optimized. Despite maintaining the logical functionality of the circuit, many of these modifications reduce the security. In some masking schemes, the order of evaluation is important to make sure that the unmasked key is never made available, and CAD tools which reorder the logic can disrupt that. Additionally, in dual rail circuits, setup time violations can cause glitches where the true value of a signal might be made available through timing information. Capacitive coupling between components during routing can cause information to leak between individual combinational components. These diagrams show 2 examples of how CAD tools can optimize security features. In the design on the left, the input and output values are the same, with a random mask value applied to make detection of the value stored in the register more difficult. The value is X XOR M, which doesn't leak any information about X. The design below is the CAD optimized version, which produces the exact same functionality and is a more efficient design, but lacks the added preventative measure. The second design, on the right, shows redundancy logic. Modification of the circuit, in the case of a fault injection attack or something similar, will be detected to cause an alarm, but in normal operation, the redundancy check will logically never pass, since the same logic is copied across the 2 branches. A CAD tool will detect this and remove the redundant logic, weakening the circuit to fault injection attacks. There are several solutions available to mitigate these issues with CAD tools. One of these is adding constraints to the design during the synthesis and place and route steps. However, these constraints must be manually added and are not always obvious. In addition, constraint format and requirements vary between vendors. There is no single standard for design constraints. A potential solution to this issue is an independent verification. The independent verification would perform checks based on the attacks that the circuit is designed to thwart. The tool would then check the success of performing these attacks. These checks could be performed in a logic level simulator. Additionally, the tool should compute some information about leakage metrics, which can be simulated using a SPICE simulator.